me on 10.2. We're talking about inscribed angles today. Really, we're going to talk about a bunch of different kinds of angles and also arcs. In a circle, an arc is like the pie crust, the pizza crust, the thing that goes around. And we measure arcs and angles both in degrees. So we're going to be talking about a lot of degree measures today. To review a couple definitions, and notation especially, we have name the circle. And remember, we always name circles by their center. So this would be circle D. And by definition, a circle is all the points equidistant, meaning the same distance away from the center. Letter B is a diameter. Again, we talked about this term yesterday. A diameter goes through the center. Oh, that's terrible. Diameter goes through the center. Splits my circle in half. So this is diameter AC. And if I split my circle in half, what I'm left with is two semicircles. So for example, this half of this circle is called a semicircle. And when we name semicircles, we're going to use arc notation. So an arc has this fancy little swoopy line on top of it. And for a semicircle, we use 3 letters because normally we would just name them by their endpoints, AC. But if I only use those 2 letters, then I don't know which half of my circle I'm talking about. So I'm going to have to name this A, B, C, and that's my semicircle. Now, a semicircle is a kind of arc, so it has a degree measurement. If a circle is 360 degrees, then the arc measure of a semicircle is going to be half of that at 180 degrees. Everybody good with that? Okay. So continuing on talking about arcs, the next arc that I see here is BC. BC is called a minor arc. And to name this arc, we only need to use 2 letters. Anytime we name a minor arc, we're only needing 2 letters. And an arc is anything less than a semicircle, which means that the measure of a minor arc is going to be less than 180. So I'm putting a little note on there. It's less than 180. So this could be something like, I don't know, this looks like it could be about 70. Let's call it that. Good? Then we have major arcs. I'm going to try to keep these colors kind of together. A major arc is any arc that is greater than a semicircle. So we're looking at a value greater than 180. So it has to at least be a semicircle and then some more. So let's say that this whole major arc would be something like 250 degrees. And to name major arcs, once again, we're going to use 3 letters. Using 3 letters helps us determine which side of my circle I'm looking at. And the order does matter here. So if I say ACB, that means this point C is in between the 2 endpoints A and B. Everybody good on those arc definitions and notation? The last little piece here is called a central angle. A central angle has a vertex on the center. So the center of this circle is D. So the vertex of this angle right here is at D. So we would call that angle. It's an angle, by the way, not an arc. So we're going to use angle notation, BDC. And that's the angle formed by 2 radii. So each one of these is a radius that's congruent. Okay? One thing that is important to know about central angles, and I'm going to make a little note on here if I can squeeze it in. Central angles equal whatever the arc measure is. So remember how I told you, let's pretend that this arc measure is 70 degrees. Well, if that arc measure is 70 degrees, then this central angle measure is also 70 degrees. So they match up. Any questions on that part? Let's do a couple examples. So I'm going to start with this circle diagram. This is a very common thing that you're going to see here. In order to do these circle diagrams, I strongly recommend you fill in literally any information that you can as you go, as you answer questions, fill it in. So the first part is angle DCX. Look at the difference between an angle notation versus an arc notation. So angle DCX is referring to this angle right here, and that's 56 degrees. That's already filled in for me. Then I look at letter B, the measure of angle YCW. Here's YCW. That is a diameter. And the measurement of a diameter is always 180 degrees. Oops. Go away. I'm not going to fill that in because we're going to need some room later. Then I have the measure of, now I'm looking at an arc notation, YMW. It being 3 letters is already telling me that this measurement is either 180 if it's a semicircle or greater if it's a major arc. So YMW is this guy right here. That is intercepting this diameter right here. So I know that this is a diameter, a semicircle. It's also 180. Maybe I'll put that little note up here like so. Letter D is the measure of arc dx. So here's where I start filling in, highlighting things that I see. Arc dx is the little pie crust of that pizza slice or pie slice. So I've got dx, which is intercepted by this central angle 56. We know the central angle is equal to the arc. So that's also a 56 degrees. YM is next. Let's see if I can change colors here. YM is this arc right here. Again, what I'm looking for is anything that's going to help me fill this in. I don't know anything about the central angle as it is right now, so I can't use that. But I can use vertical angles, and I can use diameters. So do I see anything in here that would help me find that? What do we see? Any ideas? Aubrey? What's angle C? Do we know? How do you know it's 84? Okay, let's just do that without using angle C. I know you see that diameter YW, but XM is also a diameter. So I have 2 different diameters in this problem. Let's use them the same way. If that's a diameter in blue, this whole thing is 180 on this side. So I can subtract 40 and 56 to leave me with this is, what did I say it was? 84. So this is 84. And then look I can fill in a bunch of this information now. This is 84 by vertical angles. This is 84 because of central angles. I can fill in so much information every single time. This is 84. And then the last part is XMY. I'm going to switch to my highlighter so we can actually see. XMY means that M has to be in the middle of X and Y. So that's this whole thing. It's a major arc. It's bigger than 180. We're going to add all of those pieces together. So I've got a diameter. Here's my diameter right here. So this whole section is 180 plus this 84 we just found. I believe that's 264. A diameter plus an extra little piece. Or if you would rather do, you can do 360, the whole circle, subtract these 2 parts that we don't want. A bunch of different ways we can find that. Any questions? I'm going to lead into some more definitions and theorems now. We got quite a few. So we talked about, yes, question? Angles and arcs are both measured in degrees. Okay, we'll talk about later on in this unit how to like measure them in meters or whatever it is, like actual units of length. But for right now, when we talk about arcs, we talk about angles, all measured in degrees. Good question. Okay, let's do some more definitions. We talked central angles. Central angles are when the vertex is on the center of my circle like this. We also have another kind of angle that's called inscribed, and that is when the vertex of my angle is on the edge of the circle. We just call it on the circle. And if central angles, okay, hold on. Let's go backwards. So the central angle here, we know is equal to this intercepted arc. That's what we call it, the intercepted arc. Then the inscribed angle, which is this next little definition that we have down here, is going to be 1/2 of that intercepted arc. So you're imagining you're taking this central angle and you're pulling it back like a slingshot, so that angle is getting smaller as you pull it back, okay? So here's our little formula here, that the intercepted arc, look at how that angle measure is on the edge of my circle, is 1/2 of this arc. I guess I probably should have done that in red. That's fine. You could also say that the arc is double the angle. Either way works. That's what that little theorem right there says. Any questions on that one? We use that one very frequently, hand in hand with those central angles. Okay, next. If you kind of look at these inscribed angles and their intercepted arcs, like if you turn this diagram upside down, then this kind of looks like, it reminds me of like a snow cone or an ice cream cone. That part's the cone. This is the snow cone topping on top. Okay, that's how I think of them. If we take a look at this diagram, do we see how the snow cone topping is shared by two different cones, a cone here and a cone here, but they both share that same AD ice cream snow cone topping? So that's when an intercepted arc is intercepted by two different inscribed angles, then those two inscribed angles are the same. So for example, if I say that DA is 80 degrees, then not only is angle C 40 degrees, but angle B is also 40 degrees. So you get that little M-shaped diagram, which is nice. We use those quite frequently. We're going to set things equal or congruent with this definition. Good on those ones. We're going to move on to the next page. We got a couple more. These ones are super popular ones. This is an inscribed angle of a triangle intercepts a diameter or semicircle if and only if the angle is a right angle. What that means is I have a snow cone bottom, and the top of the snow cone is one semicircle. Okay, we see how that's a semicircle? So if your snow cone is intercepting one full semicircle, then the bottom of your snow cone is a right angle. That's all this says. So if this is a diameter, this is a semicircle, this is 90 degrees. Questions on that one? Used very frequently. We love right triangles when we can use them. And then the last one here looks scary. It's not that scary. It's when I have a quadrilateral, a four-sided shape inside of a circle. So all four vertices, corners of that shape, quadrilateral, are on the circle. Then the opposite angles are supplementary. So K and M add up to 180. And L and N also add up to 180. It is not true that the opposite angles are congruent. That is a common mistake that is made. So angle L is not equal to angle N. So maybe make yourself a note. I don't want to see you setting things equal with this theorem. They are supplementary, not equal. Those are all the definitions. Are we ready for the examples? Okay. All right. So we can rapid fire through a couple of these. So like in number 1, what I'm searching for is how do I fill in this circle? If I'm looking for angle R, then I know to find angle R, I need to figure out its intercepted arc QS. So I'm going to find the arc in order to find the angle. To find the arc, 360 minus 120 minus 140 tells me that QS is 100 degrees. Once I found the arc, I know that to get to the angle, all I need to do is divide it by 2. So that angle R is 50 degrees. In number 2, here's another one of my snow cone diagrams. I've got 2 cones that are intercepting the same like snow cone top right here, which means those 2 pieces of the cones need to be equal. So I will set them equal. 9x plus 2 equals 12x minus 13. This is 15 equals 3x, or x equals 5. We need to make sure that we're reading the whole problem, because not only am I finding x, but I'm also finding the measure of TQ, arc TQ, which is the measurement of that snow cone top. So to find arc TQ, I got to figure out its angle, its inscribed angle. So I'm going to plug in 9 times 5 plus 2, which is 47, and multiply it by 2. 94. Questions on that? Keep going. These diagrams get more complicated as we go. So again, we got to make sure that we're figuring out what can we fill in these diagrams. For number 3, I'm finding the measure of angle x and the measure of angle of arc tx. So I like to highlight what I'm looking. Oh, sorry, this should be a yx actually. I like to highlight what I'm finding, just so I know. If I'm finding an arc, I know it's double the angle. So I'm going to multiply 52 by 2 to get 104 degrees. And if I'm finding an angle, I know that I'm going to divide that angle by 2. So that's going to be a 43 degrees. Nothing crazy here. Things start to get a little bit crazier in number 4. So I'm finding x, y. I'm finding arc AB, and I'm finding arc DC. I have this like M shape or this WE shape. Anytime I see that, I'm thinking, okay, there's 2 snow cones. They're intercepting the same snow cone top. There's one snow cone. Here's the other snow cone. So these 2 pieces here and here are the same. 5y minus 3 equals 4y plus 7. Y equals 10. Then to figure out the arc AB, I plug that in. 5 times 10 minus 3 is 47. Multiply it by 2 to get the arc. Good on the y's. Then I'm literally going to do the same exact thing for the x's. Both of these x angles, here's one snow cone. It's a really skinny snow cone. And here's the other snow cone. So then these 2 pieces of my angles must be congruent. 5x equals 7x minus 8. 8. So this is negative 2x equals negative 8, or x equals 4. Plug it in. This is 20. So multiply it by 2. This angle is 40. It's a lot of steps. Anybody have questions on those ones? We got a couple more we're going to do. Flip it over. These are like the big theorems. In number 5, it says find MP. Okay, well, here's MP. I don't have an angle for MP. Okay, there's no inscribed angle for that arc. So instead, what can I fill in? Well, if that angle P is 31, then I know that its intercepted arc is double it. It's 62. And then what else do I have in this diagram to help me? Casper? Yeah, I have a diameter right here. We know that the measure of a diameter is 180 degrees. So if that whole thing is 180, that little sliver MN is 62, then what's left over should be 118, 360 minus 60, or sorry, not 360, 180 minus 62 is 118. Good on that one? Number 6, again, what do I see in this picture? Right away, I should see one of these segments is a little bit more important than the other segments because it's a, what's this right here? Casper? It's a diameter. Diameters are super important. We have to look for them. That tells me that I'm looking at semicircles. So if that's a semicircle, remember, what is this angle? We have a theorem. Dahlia. It's right angle. It's 90 degrees. So again, I have a right triangle. I'm looking for the 2 angles in that right triangle. I'm going to add all of these angles up to 180. So this is 9x equals 90, or x equals 10. And then I'm looking for the measure of arc AC, which is this arc right here. And in order to find arc AC, I need to know its intercepted angle, which is B. So I'm going to plug in 8 times 10 minus 4, which is 76. Multiply it by 2, 152, I think. Okay, questions on that one? 2 more. Number 7, find x, y, and the measure of angle BAD. I promise I'm almost done. Here's a quadrilateral, a 4-sided shape. This one kind of looks like a kite. So I'm going to go ahead and say that in a quadrilateral, by that theorem, opposite angles are supplementary. So I can set up 2 different things. Remember, we are not setting them equal. If you're setting them equal, you're doing it wrong. This is 58 plus 2x equals 180. So 2x equals 122, and x equals 61. Then I also have 3y plus 4 plus 2y plus 16 equals 180. I'm squeezing it in here. And 5y equals 160. So y equals 32. And then what's the last part that I'm finding? Arc BAD, this whole guy. Oh, it's a giant snow cone top. Big old snow cone top, tiny little cone. So I need to know what's the measure of the little cone piece. That's 2 times x, which is 61, so 122. And then this is double 122. 244 is the measure of arc BAD. Questions on those ones? Okay, we have one more. We're almost done. Look it over here. Oh gosh. I'm finding in this insignia, this emblem, I'm finding the measures of angle S and angle T. What's nice is that I have a 90-degree angle. So again, those are supplementary. To add up to 180, angle S has to be 90. So this is a right angle in here. And then same thing with the T's. These 2 have to be supplementary. 14x plus 8x plus 4 equals 180. I believe that's going to give me x is 8. So then plug it in. Angle T is 8 times 8 plus 4, or 68 degrees. Okay, we did it. Any questions?